So it's my pleasure today to talk about a real demo related to what we've seen. Directionally, there's been a fantastic bit of insight shared today around how the data center is progressing and developing. So what I want to show right now is that this is real. It's happening right now, and it's happening with important applications. We're going to touch on a thing called NVMe, non-volatile memory express. So for the non-storage folks, this is a technology that's really about resolving one of the bottlenecks in the storage subsystem. It's a logical interface specification that sits between the non-volatile memory and the physical transport medium. Now, the important thing about non-volatile memory express is that it addresses some of the shortcomings that existed in the what we call the AHCI, the Advanced Host Configuration Interface. Now, this interface was, it was advanced and it was really effective and really well deployed, but it was based on the idea of spinning media. And because of that, there's some fundamental limitations when you look at using that as a logical interface format for modern non-volatile memory storage. So this is all in the context then of Rackscale design. And you've heard from Chris earlier, talking about the different capabilities, so I won't labor the point on these ones. Fundamentally, though, what we're talking about here is disaggregation, and the idea that you can build out your infrastructure based on your actual needs. The fact that we can separate out compute, network, and storage into different parts of the environment is really effective to allow you to procure at the rate that's required. The composability then allows us to pull all of that together. But it's not just about that we've disaggregated things and now we're bringing it back together again. It's about the thing that you bring back together is now customized for the workload that you want to deploy. And then the really important point that this enables is the resource utilization improvements. Because no longer are you going to have to look at having a fixed set of capacity for every workload. Now you have capacity that's targeted at your workload, and that brings the TCO savings. When we look at the Rackscale design as an overall framework and what it really means, first and foremost, I'd say it's a set of specifications. And these specifications govern the rack, the module, the data center, and the software for how everything is supposed to fit together. And it's these specifications that lead to vendor interoperability in this space, and it leads to wonderful choice and wonderful flexibility. Building on the specifications, though, what's really important as when we start looking at the implementation, it's the software and it's the open APIs aligned with the DMTF Redfish format. That's the thing that makes sure that when you want to deploy your Rackscale-based infrastructure, the orchestration environments that you need that to connect to so that you can automate your service delivery, they're going to depend on open and standardized interfaces. So now, so we've looked at infrastructure. We've heard lots about the innovation that's happening in the data center and in the infrastructure space. One of the reasons we do this kind of work is to enable the creativity that's happening in the application development space. And there's some really creative folks in the Barcelona Supercomputer Center, and they've developed an application called Smurfin. Now, if you talk about, things that are going to make a meaningful difference in people's lives, or at least we believe it will, this type of a tool is the kind of thing that does that. This is a tool that's targeted at genomic research. And it's targeted at a thing called the somatic mutation finder algorithm. It's looking at the genetic sequencing and codes to identify if there's possibilities for things like tumor or cancer-related illnesses. And what's really important when you start thinking of the bigger picture of how these kind of applications make a difference to people's lives, ultimately they're leading towards the idea that you can have very targeted medical treatment based on a very specific condition. So the kind of things that someday will likely impact all of our lives. Now, when you take the intent that people working in this type of application are trying to do, and they want to deliver it effectively and efficiently and fast, it has to be responsive to deal with the quantity of data they need to assess. Step forward Rackscale design and the idea of composability. In this specific case, one of the characteristics of this application is that there's a really significant sized input data set. It doesn't really impact the performance of the workload itself, but the output data set does. And they need about 100 gig of a volume capacity to be able to write all of their output data. And it turns out that it's really important that that is very fast, that storage, that write capacity. So fundamentally, NVMe, because it's moved away from or reduced the bottleneck in the storage subsystem dramatically, it's allowed for a dramatic performance improvement here. Combine that with the actual non-volatile storage technologies. So what I want to show, and I'm going to have to move to the back of the room to show a demo on this, but what I want to show with this environment is two different models. Excuse me. Sorry. There are two different scenarios that we've set up in the lab. And the first scenario is going to look at, firstly, the idea that if you have this really fast capacity in your environment, you've got the NVMe-based target and it's connected to a storage device, and that's built right onto the first chassis that we'll look at, or the first compute node. So, yeah, when you do that, if you may switch back just for a moment, because I just want to highlight the top right-hand corner. When you do that, what we talk about is this idea of a stranded memory, stranded local NVMe memory. And it's stranded because it's really only fit for or accessible to the workload that's running on that server. Now, there's a second scenario we want to introduce then, and that's looking at the idea that you've got a shared NVMe. So it's taking all that goodness of this NVMe logical protocol and being able to access it over a network. Now, why would you want to even do this? Well, start with some fundamentals. The storage device that you want to connect to is probably a 400 gig device. Now, if you're going to pay for a 400 gig SSD to be sitting on your platform connected over an NVMe or target, you really want to be getting some value out of that expense. So when you move to an NVMe over Fabric model, and you can have that single SSD with 400 gig capacity, and then we'll look to break that up into multiple volumes so that we can share that investment. Now we can drive multiple instances of this same workload, which hopefully we all agree is really important, and we can get that same workload running really effectively and delivering an output that for the same instance works in approximately the same time, but when you look at the way you can expand this at scale, it's far more efficient. So maybe I'm going to switch over to my PC screen here. And the bars that we're showing here, that top red one, that's focused on that stranded local storage. Now you can see the right I/O column, the sort of middle column in text. That's the current speed that this demo is running at. It's writing out to the SSD. Now that goes up and down depending on what exactly the application is doing at the time. The really important point here, though, is the right-hand side column where it shows the average run rate. Now, the other three are that second scenario I mentioned. This is where you've got 3 instances now of the Smurfin demo running, all connected to, or leveraging a volume that's coming out of an NVMe over Fabric target on a single SSD, 400 gig capacity. And you can see, if you look at the average run rates, they're approximately 30 minutes. Give or take a 5% difference between the locally attached dedicated storage that's going to cost you, or the really efficient NVMe over Fabric accessible through composability. Now, what I'd like to do is switch over then to show you how you actually enable this at scale. Because the technology itself is wonderful, but if you can't deliver it at scale, where scale doesn't just mean the number of nodes in your data center, it means how easily you can adapt to an expanding data center and how can you automatically consume that capacity. And this is really one of the value propositions of Rackscale design. It's the manageability that comes from the Redfish-based open API interface. This GUI that we're going to show, hopefully you can see my cursor. First up, a dashboard that gives you sort of an insight into what's available in the environment. So you've got, in this case, it's a single pod with a single rack. You can see the number of compute systems or sleds that are in the environment. You can look at the total NVMe capacity that's available in this environment. Down here, we get to see how much of that's actually being consumed. And if I scroll down a little bit more, and you see it's so easy, I can even do it single-handed, that we've got our 5 nodes composed, and we've got the health status. So everything is running perfectly. Now, by the way, we're connecting over the same Wi-Fi as everyone here, so responsiveness is a little slow in this demo. What we see up here is the current set of composed nodes. So and you can click into these and you can have a look at what actually has been configured in the environment. You can get a full view on the config space. You can have a look and see what your storage-related allocations are. As we scroll down, you can look at the actual volumes that are connected. Well, actually in this context, on this GUI, the base pool really represents a single instance of an SSD. And if we were to connect into this, it's a larger capacity device where we've got 300 gig worth of volumes. And you can see up here on the right-hand side, a little hard to read this text, but what that says is that we've already defined 3 different volumes in this environment. So now, if we're to look at comparison or bringing it back to the graph I just showed you, that local NVMe is running here, and you can see we've got a large input volume set. And if I look down at the volume data, see that we've got 1,000 or 1 terabyte device. When we look here at the different remote capabilities, and we again looking at the volumes, we can see our target volume here is 100 gig. Now I want to show you how easy it is to add that type of volume to a running instance. So here I've got the capability to go and edit a particular composed node. Let's say I just want to give it a 40 gig volume. Now this exists, if you see here in the link, it exists in one of those volume or storage pools that I pointed at. It is a live demo, so I'm going to connect to the system. And if I have a look at the... Okay, you can see I've just attached a 40 gig device here. Now, if we jump back in here, it just takes a moment now for the screen to refresh. Okay, so there you can see it up here in the GUI now. We're showing that the 40 gig device was attached. And similarly, if your needs change and you need to update your capacity or you want to allocate some volumes to different use cases, it's quite a straightforward process then to detach that. So if we look again at the block interface, we can see the 40 gig volume has been removed. So that's for a running system. But what about you want to compose it from the start? Actually, just give this a moment. So the composition from the start, this is where you get into the full set of being able to target a particular compose node for your use cases. So we can just go up here and we can start to compose a new node. I'm going to give it a name. Now, part of this type of capability you've got is be able to specify what exactly you're looking for. In this environment, we've got some Xeon E5s set up. You can go and specify what kind of memory speed you'd really need in your environment. And when you start thinking about the scale of a data center where you have heterogeneous deployment with different types of compute sleds in your environment, this is where you start to be able to pick up on that value and be able to compose a node based on what you're really looking for. In this case, we're looking at an NVMe over Fabric config that we want. So we'll use one of the existing configured volumes. Let's give this one 500 gig. And then also, what kind of network do we need? Again, the environment here, we've got a 25 gig Fabric established. Okay, so now with that, the compose node has popped up here in the GUI. Just give it a moment and it'll start to connect the drive. While it's doing that, let me just log into it. And you can see there we've just attached a 500 gig device. So, okay, with that, we can switch back to the other screen. Right, so what we've shown here is the 2 different scenarios. We've done the looking at the top one where it's locally attached, and then the shared pool. So if we, let me just move on here. And I left my clicker after me. It's a long walk back. Thank you. Okay, so I want to show the performance difference in more graph terms. So at the top here, we looked at okay, we've got a really high performance device, like I mentioned. And you can see here with a single instance of an application running, you're not really using the max capacity of that device. So not only are you not using the full breadth of its storage capacity, you're also not using the performance that NVMe really offers up. On the bottom one, because we've got multiple targets, we've got multiple instances of the application all targeting that same SSD over this fabric, now we start to go and push the real performance potential. And as you can see, because the application, it's doing writes, the different instances are doing writes at slightly different times. You don't really need to have 3x the I/O capability. Like in the top case, you're at 1.5 gigabytes per second type of an I/O. In the bottom case, you're getting close to 1.8 as a kind of a top out point. But as we can see from the average completion throughput, that's perfectly acceptable. Well, for most cases at least, it's going to be perfectly acceptable for the environment. We're, like I mentioned, about 5% difference between the direct and the remote. So, so with that, really I think what the key takeaway for me is that there are these applications that are really important, that we want to make sure can run effectively and efficiently in an environment. Rackscale, combining the capability of disaggregation with composition, with the management solutions to manage these things at scale, allows you to really benefit and allows those applications to really benefit from a modern, advanced infrastructure. I would encourage you, if you're interested in this type of use case and others related to storage optimization, and particularly looking at how we leverage pooling at scale, then please reach out to your RSD solution manager. Talk to the folks that have been actively involved in this project. Talk to the folks at SafeDX and at Foxconn and at all of the partners that we have working in this space. With that, thank you very much.